Ancient asteroids reveal that the early solar system was more chaotic than we thought. This is by Evan Gu, Universe Today on Science Alert. There's no question that young solar systems are chaotic places. Cascading collisions defined our young solar system as rocks, boulders, and planetesimals repeatedly collided. A new study based on chunks of asteroids that crashed into Earth puts us into a timeline to some of that chaos. Astronomers know that asteroids have remained essentially unchanged since their formation in the early solar system billions of years ago. They're like rocky time capsules that contain scientific clues from that important epoch because differentiated asteroids had mantles that protected their interiors from space weathering. But not all asteroids remained whole. Over time, repeated collisions stripped the insulating mantles away from their iron cores and then shattered some of those cores into pieces. Some of those pieces fell to Earth. Rocks that fell from space were of great interest to people and were a valuable resource in some cases. King Tut was buried with a dagger made from an iron meteorite, and the Inuit people in Greenland made tools out of an iron meteorite for centuries. Scientists are keenly interested in iron meteorites because of the information they contain. A new study based on iron meteorites, which are fragments from the core of larger asteroids, looked at isotopes of palladium, silver, and platinum. By measuring the amounts of those isotopes, the authors could more tightly constrain the timing of some events in our early solar system. The paper, quote, "The dissipation of the solar nebula constrained by impacts and core cooling in planetesimals," end quote, was published in Nature Anatomy. The lead author is Alison Hunt from ETH Zurich and the National Center of Competence in Research, NCCPR, Planets. Previous scientific studies show that asteroids in the solar system have remained relatively unchanged since their formation billions of years ago, Hunt said. They, therefore, are an archive in which the conditions of the early solar system are preserved. The ancient Egyptians and the Inuit did not know anything about elements, isotopes, and decay chains, but we do. We understand how different elements decay in chains into their elements, and we know how long it takes. One of those decay chains is at the heart of this work, the short-lived lead 107 lead and 107 silver decay system. I'm trying to remember my chemistry. PD is lead, Ag is silver, right? The chain has a half-life of 6.5 million years and is used to detect the presence of short-lived nuclides from the early solar system. The researchers gathered samples of 18 different iron meteorites that were once parts of the iron cores of asteroids. Then they isolated the palladium, silver, and platinum in them and used a mass spectrometer to measure the concentrations of different isotopes of the three elements. A particular isotope of silver is critical in this research. During the first few million years of the solar system's history, decaying radioactive isotopes heated the metallic cores in asteroids, and as they cooled and more of the isotopes decayed, an isotope of silver, 107 Ag, accumulated in the cores, and the researchers measured the ratio of 107 Ag to other isotopes and determined how quickly the asteroid cores cooled and when. This is not the first time researchers have studied asteroids and isotopes in this way, but earlier studies did not account for the effects of galactic cosmic rays, GCRs, on the isotope ratios. GCRs can disrupt the neutron capture process during decay and can decrease the amount of 107 Ag and 109 Ag. These new results are correlated for GCR interference by also counting platinum isotopes. Hunt said, "Our additional measurements of platinum isotopes abundances allowed us to correct the silver isotope measurements for distortions caused by cosmic irradiation of the samples in space. So we were able to date the timing of the collisions more precisely than ever before." Hunt said, "And to our surprise, all the asteroidal cores we examined had been exposed almost simultaneously within a time frame of 7.8 to 11.7 million years after the formation of the solar system. A 4 million year time span is short in astronomy. During that brief period, all of the asteroids measured had their cores exposed, meaning collisions with other objects stripped away their mantles. Without the insulating mantles, the cores all cooled simultaneously. Other studies have shown that the cooling was rapid, but they could not constrain the time frame as clearly. For the asteroids to have the isotope ratios the team found, the solar system had to be very chaotic a place with a period of frequent collisions that stripped the mantles from asteroids. And she says everything seems to have been smashed together at that time, and we wanted to know why. Why would there be a period of such chaotic collisions? There are a couple of possibilities according to the paper. The first possibility concerns the solar system's giant planets. If they migrated or were unable somehow at that time, unstable, they could have reorganized the inner solar system, disrupted small bodies like asteroids, and triggered a period of increased collisions. The scenario is called the NICE model, N-I-C-E. The other possibility is gas drag in the solar nebula. When the sun was a protostar, it was surrounded by a cloud of gas and dust called the solar nebula, just like other stars. The disk contained the asteroids, and the planets would eventually form there too, but the disk changed in the solar system's first few million years. At first, the gas was dense, which slowed down the motion of things like asteroids and planetesimals with gas drag, but the sun got going. It produced more solar wind and radiation. The solar nebula was still there, but the solar wind and radiation pushed on it, dissipating it, and as it dissipated, it becomes less dense, and there was less drag on objects. Without the dampening effect of dense gas, asteroids accelerated and collided with each other more frequently. According to Hunt and her colleagues, the reduction of gas drag is responsible. Co-author Maria Schonblacher explains the theory that best explains this energetic early phase of the solar system, indicated that it was caused primarily by the dissipation of the so-called solar nebula. And this solar nebula is the remainder of gas that was left over from the cosmic cloud out of which the sun was born. For a few million years, it still orbited the young sun until it was blown away by solar winds and radiation, Schonblacher said. She said, our work illustrates how improvements in laboratory measurement techniques allow us to infer key processes that took place in the early solar system, like the likely time by which the solar nebula had gone. Planets like the Earth were still in the process of being born at the time. Ultimately, this can help us to better understand how our own planets were born, but also give us insight into others outside our solar system. This was published originally on Universe Today, and it's on Science Alert. Please leave your comments. Thank you. Support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.